Marhaba. Okay, in this video and the subsequent ones, we want to study the notion of a mathematical proof. And we want also to study different strategies and techniques in writing mathematical proofs. Okay, let's recall that we have an idea of what is a proof, which previously we studied the notion of formal proofs. Okay, and remember, what were formal proofs? They were sequences of statements in propositional logic or predicate logic, where each sentence in the sequence is either a premise of the argument that we wanted to prove its validity, or this sentence in the sequence is inferred from previous statements by a rule of inference. Okay, but the problem of, we have several problems with the formal proofs, is that first, say, we need to supply all steps of this proof. So we need to supply every single statement in this sequence. So we need to supply all steps. So it's tiring and time consuming. We also need to justify like which rule of inference was used at each step. So we need to justify each step. What else? Like we need these proofs could be extremely long. Okay. And all of this will make it very difficult to be followed by humans. Okay. So like formal proofs have these problems to us as humans. It's difficult to read them, and we need to justify each step, and we need to supply all steps, no matter how trivial they are. But still, formal proofs are very important. For example, in the area of mathematical logic, we need formal proofs in mathematical logic, and they are also used in artificial intelligence. For example, in the when we build what we call automated reasoning systems. Okay. Automated reasoning systems. So, like, to solve these problems, we want to write what we call informal proofs, or proofs that we use in everyday mathematics. Now, what are these proofs? In the concept, it's the same concept, but we write them in a different way. So let me explain. So in everyday mathematics, like, let me call them informal. We write informal proofs, and what we use, we don't use the symbolic language of logic. We use our natural languages. So here we use natural language to write our proofs. For example, we can use English, Arabic, Russian, Greek, Urdu, Hindi, Mandarin, any natural language you want, you can write your mathematical proof with. And then we write it in a way to be clear or very suitable for human consumption. Suitable for human consumption. So we want, when humans read the proof, it will be clear and understandable. We might apply different several steps at once. Okay? Instead, like in formal proofs, we need to supply all steps. But in our informal proofs, we can apply more than one rule of inference at a single step. So apply more than one rule of inference at once. And we also don't need to justify which rule of inference was applied. Okay, so we can not explicitly state which rule of inference. So avoid. We don't need to state explicitly which rule of inference was used at each step, and of course we can skip obvious steps. So we want our proofs to be written in a way to be very clear and understandable when humans write our proofs, read our proofs. Okay, now before we start, so later on I will describe clearly what is a mathematical proof. But this is, so the idea is that we want to move from formal proofs, which have many obstacles for understanding them, easily understanding them by humans, to informal proofs where we will use our natural language to write them. And before going to defining what is a proof, mathematical proof, let's just introduce several terminology in the area of mathematics. So let's first introduce the term theorem. What is a theorem? So a theorem is a statement in mathematics. So is a statement in mathematics which is shown to be true by providing a proof, by writing down or providing a proof. And we will say what is a proof precisely in a few minutes. Okay, we also call theorems, so these statements which we proved to be true by writing down a proof, they are also called like results or facts. Okay, so we have results, facts, theorems. All of these nouns or terms represent statements, talk about statements which we proved them to be true. Okay, now what is a lemma? Well, a lemma is a minor theorem, and by minor I mean less important than the main result, than the main theorem, which is used in the proof of a more important theorem. Okay, so what is a lemma? It's a theorem. It's a statement which we prove to be true by writing down a proof, but we anticipate that we will use it, or it will be used in the proof of another theorem. So it's just a different terminology for a less important theorem that will be used in the proof of a more important theorem. Okay. Now a corollary. What is a corollary? It's a statement in mathematics which is an easy consequence of a theorem. Easy consequence of a theorem. So suppose we proved a theorem, like we have a statement which we proved to be true by writing down a proof, and then an easy consequence of the statement we proved was written down, and this consequence we call it a corollary. For example, suppose we proved that every person in this class has a smartphone, and Fairuz is one of the students in this class, then an easy consequence of our theorem is that Fairuz has a smartphone. Okay, so next, a conjecture. What is a conjecture? So a conjecture is a statement which is proposed to be true, which it's a statement. So is a statement which we think it might be true, but we still don't know. Okay. Which is proposed to be true, but not proven yet. Yeah? But has not been proved yet. Okay, what do I mean by this? I mean, we have a statement and we don't know whether it's true or false. So it is, if you want, in other words, it's an open question. And the dream is to either prove it or disprove it. If we prove it by writing down a proof, or we refute it by showing it's false. And we will see examples of conjectures, like some conjectures takes hundreds of years to be solved. And finally, we want to introduce the term which is an axiom. Yes. So an axiom is a statement which we consider, we assume it to be true. Okay, it could be true or false, but in our setting, in our domain where we are working, we take it to be true. We assume it to be true. So it is a mathematical statement that is assumed to be true. So when you say these are my axioms, it means that we are assuming that we are working in domains where these axioms are true. So we will see examples of all of these terms. So again, just quickly, we introduced a theorem. It's a statement which is shown to be true by providing a proof. We will write a mathematical proof to show that this statement is true. A lemma, it's a less important theorem which is used in the proof of a more important theorem. A corollary is an easy consequence of a theorem. A conjecture is an open question. It's a statement which we don't know whether it's true or false. And in mathematics, we do research to write down a proof to find out a proof which will show that conjecture to be true, or to refute it, to show it is false. And then axiom is a statement which we assume to be true. Okay? So in other words, we work in domains or in where our axioms are true. Okay, so let's have just quick examples of these. So for example, you are very familiar with famous theorems in mathematics. You have the famous Pythagorean theorem. Okay, so this is a theorem, which it's a statement which was proven to be true. The statement of the Pythagorean theorem says, in any right angle triangle with sides AB and hypotenuse C, we have that A squared plus B squared is equal to C squared. And I encourage you to look at many proofs of this theorem. Another famous theorem in mathematics is the fundamental theorem of calculus, which relates the integral and the derivative of continuous real valued functions. Okay, in this course, we will present the fundamental theorem of arithmetic and prove it, which says the statement of the fundamental theorem of arithmetic says that every positive integer bigger than 1 is either a prime or can be written as the product of primes in a unique way. We will also prove another theorem we will see in this course. It's the statement which says there are infinitely many prime numbers. We will prove that there are infinitely many primes. The prime numbers never stop. They will continue forever. Okay, so these are examples of statements in mathematics which we provided a proof for to show they are true, and we call them theorems. Okay, now let me give you examples of axioms. So I want to tell you axioms for our everyday arithmetic in mathematics. So axioms describing addition and multiplication. So usually these axioms are describe mathematical structures called rings or fields. But you are familiar with these, like for an example of a ring is the integers with addition and multiplication, and an example of a field is the real numbers with addition and multiplication. So let me tell you what are these statements which we assume to be true in these domains. So let's say, for example, look at the axiom of additive identity. So additive identity. What does this axiom say? For every element in the domain, if you add this element to 0, you get the same element. So this is the axiom that describes the role of 0. It says that adding any element to 0, you get the same element. We have the additive inverse axiom, which says every element in the domain has an additive inverse. So for every element x, there exists an element y, such that if we add x and y, we get the additive identity 0. We have addition commutativity, which says for every element, if you want for every number x, for every number y, when you add x and y, it is the same as adding y and x. So the order of addition doesn't matter. Okay, now we have also addition associativity. Okay, what does it say? It says choose any 3 elements in the domain. So for every x, for every y, for every z. I will write it here. Okay, so for every x, for every y, for every z. If we add x and y first and then add the result to z, you get the same number as adding first y and z and then adding x. Okay, so associativity say it doesn't matter when you add 3 numbers, it doesn't matter which 2 you add first. And we also have like axioms describing multiplication. For example, we have the multiplicative identity. The multiplicative identity axiom, okay, which says if you choose any number and you multiply this number by 1, you get the same number. We also have the multiplicative inverse axiom, which says every element, non-zero element has a multiplicative inverse. So for every element, there is a y such that if x is not 0, then x times y is 1. Okay, for example, in the real numbers, this axiom is true that any non-zero real number has a multiplicative inverse. The multiplicative inverse of 3 is 1/3, and the multiplicative inverse of 1/5 is 5. Okay, what else? Okay, we have the axiom of multiplication commutativity. If you multiply x times y, you get the same number as y times x. And we have multiplication associativity also. And we have distributivity. So the axiom of distributivity, what does it say? It relates the two operations together. It relates addition with multiplication. It says for every x, for every y, for every z, if you choose any three numbers and you multiply x with the sum of y and z, this number is the same as multiplying x with y and then adding the result to the multiplication of x times z. Okay. So you can say these are my axioms, which means I am working in domains where these axioms hold true. Okay, so distributivity axiom. So these are axioms in mathematics. Okay. Now let's talk about conjectures, examples of conjectures. So how do we arrive to conjectures? Well, for example, one way is noticing that a specific pattern holds true for numerous cases. So once you see that this pattern arises, you can conjecture or you can guess that this pattern will hold for all the cases, but usually we have infinitely many cases. So you say, okay, I have this conjecture, or I am proposing that this pattern will hold true for all the cases, but we still don't know if this is true or false. So if it's true, we need to write down a proof. If it's false, we need to find, say, one case which doesn't, where the pattern doesn't hold. And we call this case a counterexample. Another scenario where we conjecture, like where we propose a statement to be true, is by intuition. Say we have our intuition, or the intuition of an expert or a very brilliant mathematician thinks that this statement will be true, or they are proposing, he or she, they are proposing that the statement will be true. But of course, it's still an open question whether it's true or false. We need to prove it or disprove it. And so both cases could happen. Like in history, some conjectures were proven to be true and other conjectures were refuted. We proved they are false. So our intuition could be false, and our observation that the pattern holds for some cases, it turns out that it doesn't hold for all the cases. So let's take two examples of very famous conjectures in mathematics. Let's start with what is called Ferma conjecture. Okay, so here is Fermat's conjecture. So now let's talk here. We work in the domain. To state it, we work in the domain of positive integers, say 1, 2, 3, 4, and so on. Before stating the statement of the conjecture, let me do some motivation. So can we find positive integers such that x, y, z? So is the statement true or false that there exists an x, there exists a y, there exists a z, such that x plus y is equal to z, where the domain of x, y, z is the set of positive integers? Well, this statement is true. In the positive integers, we have even infinitely many witnesses for x, y, z. For example, you can choose x to be 1 and y to be 4 and z to be 5. 1, 4, 5 satisfy this property that x plus y is equal to z. Now, what happens if we change the exponents of the variables to 2 instead of 1? So what is this statement, true or false, in the domain of positive integers? So there exists a y, there exists an x, there exists a y, there exists a z, such that x squared plus y squared is equal to z squared. Well, this is also famous equation, and we have witnesses for x, y, z satisfying this equation. So here is x, here is y, here is z. You can take the famous triple 3, 4, 5, right? 3 squared plus 4 squared is equal to 5 squared. Okay, another triple is 5, 12, 13. 5 squared plus 12 squared is equal to 13 squared. Now, let me also tell you that if you have these triples, x, y, z, which satisfy the equation x squared plus y squared is equal to z squared, are called Pythagorean triples. So this triple and this are called Pythagorean triples. It turns out that we have infinitely many Pythagorean triples. Just consider any one and multiply it by a fixed positive integer, say k, then you get another Pythagorean triple. So for example, 3k, 4k, and 5k is a Pythagorean triple where k is a positive integer. Okay, so for example, when k is 2, we get 6, 8, and 10 is another Pythagorean triple. Okay, and this fact was known since antiquity. The ancient Greeks knew these facts. Now the question is, what happens when we change the exponent to 3 or more? So here the story comes. It started with the French lawyer and mathematician. So French lawyer and mathematician. His name is Ferma. Okay. Pierre de Ferma, sorry. Okay, and what he did is that in one of his mathematics book, he wrote in the margin that the let me write what is Fermat, what is the conjecture, what is Fermat's conjecture. He wrote that there are no positive integers x, y, z such that x to the n plus y to the n is equal to z to the n, where n is positive integer bigger than or equal to 3. So he said when we change the exponents of the variables to 3 or more, like x cubed plus y cubed is equal to z cubed, or x to the 4 plus y to the 4 is equal to z to the 4, we can't find positive integers satisfying these equations. And he said that the margin where he wrote this note in his, he was reading a book, and a mathematics book, and in the margin he wrote this, and he said this margin is too small to contain his proof. And then after he died, the people collected his works and started looking at his notes. And so this was in 1637, he wrote this conjecture. And then it took generations of mathematicians to solve this conjecture. I mean, to prove it or disprove it. Actually, it was proved, so it took up to 1995 to finally find a proof of this conjecture. So it took like 358 years to settle down this open question. So when we found when this question was found, we didn't know whether it's actually true or false. So generations of mathematicians worked hard to prove it, and in this time, many mathematicians who were working on the problem, they introduced new tools in mathematics, and even they introduced new areas in mathematics for algebraic theory. So new areas like algebraic number theory. And like this conjecture, so this conjecture, Fermat's conjecture, is the one with the largest number of unsuccessful attempts, which means like during this period of time, whenever a mathematician announces that they found a proof for this conjecture, it turns out that their proof has an error or a mistake, and so we have many unsuccessful attempts in proving this theorem. Okay. Now let me tell you how the theorem was settled down. In 1994 or in 1993, the English mathematician Andrew Wiles, who worked on this problem for years in secrecy and in solitude. He announced in 1993 in a talk in Isaac Newton Institute of Mathematical Sciences in the University of Cambridge. So in the Isaac Newton Institute of Mathematical Sciences, he gave a talk and presenting his proof of the Ferma conjecture. But then, when mathematicians started reading and referring his proof, they found a mistake. And at this point, so a mistake was found. And at this point, his former student, Richard Taylor, joined him to fix this. So Richard Taylor joined Andrew Wiles to fix this error, and they managed to do it in 1994. They submitted their work, and it was officially published in 1995 in the Annals of Mathematics. They published a proof showing that Fermat's conjecture is a true statement, and it became known as Ferma last theorem. So now we need to, it was a conjecture at some point, but since it was proved in 1995, now we call it Fermat's theorem, but I'll tell you why it's called last theorem, which says when the exponent is 3 or more, we can't find positive integer solutions. Okay, why it is called last? Because Ferma used to, the French mathematician Pierre de Ferma used to write many notes in the margin of his books without giving the proof, and all of them were proved except this last one. And because it was the last one to be proved, it is called now Fermat's last theorem. Okay. Let me also tell you another famous conjecture in mathematics in the area, also in the area of number theory. It's called Goldbach conjecture. And this is from 1742. It was proposed by the German mathematician Christian Goldbach in his letters to the Swiss mathematician Leonhard Euler. The conjecture says that every, so here is the statement, every even integer greater than 2 is the sum, can be written as the sum of two prime numbers, is the sum of two prime numbers. And so this is the statement. We don't have a proof of it yet. It's still an open problem, and we don't have a counterexample. We couldn't find an even integer which cannot be written as the sum of two primes. So let me just explain the statement by going through even numbers. So we start by the first even number bigger than 2 is 4, and it can be written as 2 plus 2, and 2 is a prime number. 6 is 3 plus 3. 8 is 3 plus 5. 10 is 5 plus 5. 12 is 5 plus 7. 14 is 7 plus 7, and so far all the even numbers that were checked by the computers managed to be can be written as the sum of two primes. But we still till this current day of this date of this video, this statement is still an open question in the area of mathematics. Okay. So now I think we are ready to define what is a mathematical proof. So let me just define in a clear way what do we mean by a proof in mathematics. So a proof of a theorem beta. So suppose beta is just any statement in mathematics. For example, there are infinitely many primes, or square root of 2 is an irrational number. Just choose any statement. A proof of this statement is what? Is a sequence of statements. Let me say that, let me denote these statements by alpha 1, alpha 2, say alpha I, and so on up to the last one, alpha M. Okay, and what do we know about these statements in this sequence? Okay, where the last one, alpha M, is the statement beta that we want to prove. And each alpha I, like each statement in the sequence, is either, okay, so each alpha I is either an axiom of that we are, suppose we are working in domains where the axioms are assumed to be true. So each alpha I could be an axiom, or it could be inferred from previous statements in the sequence by a rule of inference. So very similar to formal proofs. So inferred by a rule of inference. Or this statement in the sequence could be a hypothesis itself. So any hypothesis. So I mean, if beta is a conditional statement, then we can use its hypothesis in the proof. Okay, or it could be this alpha I, it could be a statement that we deduced by applying a previously proved theorem. So we can use previously proved theorems. Okay. So this state number 4 says this alpha I, like a statement in the sequence, could be a previously proved theorem. Remember, what is a theorem? It's a statement which we showed it is true by providing a proof. Okay, so this is what is a proof, but let me say one final comment. So here is the proof. It's a sequence of statements. Okay, this sequence of statements is written in our natural language. So a proof, this proof, so this proof, which is a sequence of statements where the last one is the theorem beta we want to prove, and each one in the sequence is either an axiom or a previously proven theorem, or inferred by previous ones using a rule of inference, or it's a hypothesis. Like this sequence is written, so let me write this here. A proof in mathematics is written in our natural languages okay, we using punctuation marks and complete sentences forming and complete sentences forming clear, understandable paragraphs. So at the end of the day, this sequence, alpha 1, alpha 2, up to alpha m, will be written in our natural languages in the form of clear sentences forming understandable paragraphs. So we will read paragraphs when we write down our proofs. So in the next videos, we will learn different techniques for proving theorems in mathematics.